Hidden within a compact motor room, a single device holds entire skyscrapers still. This is the brake, the unglamorous guardian that made vertical cities possible. In this chapter, we map the anatomy. An elevator brake looks small, but it must arrest loads of 10,000 pounds or more in fractions of a second, repeatedly, without fail. The central components, the rotor or drum, the friction lining, a caliper or shoe assembly, the actuation mechanism, and redundant springs for fail-safe engagement. Modern traction elevators usually put a disc brake on the motor shaft, clamping at 0 speed to hold the car. Machine room-less designs tuck that braking assembly beside a geared or gearless traction sheave. Safety gear and mechanical governors live in parallel, ready to clamp the guide rails if overspeed occurs. Materials matter. Hardened steel rotors for dimensional stability, composite friction pads engineered to withstand high surface temperatures, and springs heat-treated to retain set after millions of cycles. We will visualize the invisible forces, clamp pressure in pounds per square inch, the microscopic contact of asperities that produce friction, and the instantaneous conversion of kinetic energy to heat. This is the logic of making a brake that never lets a city fall.
Every brake begins as raw matter, iron ore, alloying elements, and engineered composites. We follow the transformation. Steel and cast iron start as mined ore, smelted in electric arc or blast furnaces at temperatures above 1500 degrees Celsius. Molten metal is desulfurized, alloyed with chromium, molybdenum, or manganese for strength, then poured into molds for rotors or forged and blanked for calipers. Brake shoes require friction material. Modern formulas are composite mixes of resin, aramid fibers, metallic powders, and mineral fillers engineered to withstand surface temperatures that can spike to 200 to 300 degrees Celsius during emergency stops. Springs start as high-carbon or chrome silicon wire, then formed and heat-treated to hold precise preload. Fasteners are high-strength steel, often zinc-plated or stainless for corrosion resistance. Manufacturing begins with material certification and mechanical property tests, tensile strength, hardness, and chemical composition. Why this rigor? Because a rotor that warps at high heat or a spring that relaxes after 1 million cycles becomes a hazard. The brake is only as reliable as its materials, and those materials are the reason elevators scaled cities upward safely.
To stop a car, you need a stable, true rotor. This chapter follows the fabrication of rotors and brake drums. Castings start with pattern making, green sand molds, and controlled pourings. For high-performance rotors, we prefer forged and CNC machined blanks. Forging compresses grain structure, producing parts that resist cracking under thermal shock. After forging, parts go to CNC milling centers. Tolerances are tight. Runout must be within a few thousandths of an inch to avoid vibration during braking. Surfaces are finish ground to optical flatness, and critical bores are reamed, then measured with coordinate measuring machines. Heat treatment follows, quenching and tempering to reach specified hardness, often on the Rockwell scale, measured and verified. Some rotors receive thermal coatings or ceramic layers to enhance heat dispersion. Balancing is vital. Rotors are spin balanced at speeds above 1,000 revolutions per minute to detect mass imbalances that would cause cyclic loads. Finally, rotors undergo dimensional inspection, magnetic particle inspection for cracks, and a trial assembly to verify fit. Each step protects one outcome: consistent, repeatable deceleration without catastrophic failure.
Friction linings are the secret chemistry behind predictable stops. This chapter dives into their manufacture. Ingredients are measured by weight and mixed in controlled mills: phenolic resins, aramid fibers, metallic powders for thermal conductivity, and abrasive fillers for bite. The mix is hot pressed under high pressure and temperature to polymerize the resin and lock the fibers, then cured in ovens to stabilize friction characteristics. Thickness tolerances are held to tenths of a millimeter because pad wear determines service life. After curing, pads are ground to precise profile, grooved to remove gases and dust, then bonded to steel backing plates using high-strength adhesives and rivets. Each pad undergoes friction testing on a dynamometer, simulated stops at various speeds, measured wear rate, coefficient of friction stability over temperature, and fade resistance up to surface temperatures of 200 to 300 degrees Celsius. Environmental tests include humidity cycling and salt spray to ensure long service in coastal buildings. The payoff is simple: a pad that keeps friction predictable, so the brake response is linear and safe, ride after ride.
A brake only works when commanded. This chapter explores actuators, sensors, and control logic that make brakes deterministic. Electromechanical solenoids and spring-applied, electrically released mechanisms are common in elevator brakes. Their coils must generate sufficient force to overcome spring preload. In electric brakes, the motor's brake is held open by energized coils. Loss of power triggers the springs and closes the brake. Modern systems add redundant position sensors and microcontrollers to verify commanded states. Speed governors monitor cable speed through centrifugal mechanisms or electronic encoders. If the governor senses overspeed, it trips safety gear and signals the brake system to lock. Control logic handles timing. Apply friction pads gently for parking or sharply for emergency stops, and coordinates with the drive inverter to modulate motor torque during deceleration. Invisible to riders is the electron flow. Amps through coils, voltage ramps from the inverter, and pulse width modulation controlling actuation speed. All signals are monitored against safety standards, with watchdogs and redundant circuits to prevent single-point failures. The result? The brake clamps exactly when needed, every time. The brake is one link in a chain that moves people. Here we follow hoist ropes and sheaves and how braking interacts with them. Hoist ropes are wire ropes made of multiple steel strands, each strand created from drawn wire and twisted to precise lay patterns. Ropes are sized to carry loads of 10,000 pounds or more, with safety factors often exceeding 12-to-1. Ropes wrap over sheaves, grooved wheels, whose diameters must exceed a minimum multiple of the rope diameter to prevent fatigue, commonly more than 20 times the rope diameter. Sheaves are precision machined, crowned, and polished to distribute wear evenly. When a brake clamps the motor shaft, dynamic loads transfer through the drive sheave into rope tension. Sudden stops can spike local stresses and heat. That is why modern systems use controlled deceleration to spread kinetic energy conversion between the motor, braking system, and sometimes regenerative drives. Maintenance includes rope inspection for broken wires, sheave groove profiling, and lubrication to reduce friction. The mechanical harmony among ropes, sheaves, and brakes is what keeps elevators smooth, quiet, and safe in tall buildings. Assembly turns parts into a safety system. On the line, technicians mount rotors and brakes to motors and gearboxes with precise torque and alignment. Mounting surfaces are cleaned, and dowel pins locate components to avoid shear loads. Torque wrenches set bolt preload to specification, often in foot-pounds or newton-meters, and fasteners are checked with calibrated tools. Brake faces are bedded in using controlled break-in cycles to mate the pad material to the rotor surface, reducing glazing and assuring consistent friction. Actuators and sensors are connected and calibrated. Encoder pulses per revolution are verified, and limit switches are adjusted to match car travel endpoints. Many manufacturers use jigs and laser alignment tools to control concentricity and parallelism within thousandths of an inch. After assembly, the unit is run on a test bench. The brake must hold simulated loads, release under power, and perform emergency stops repeatedly over thousands of cycles. All data is logged for traceability. The assembly line is where engineering tolerances become workmanship. A misaligned bolt or an improperly bedded pad can turn engineering excellence into a maintenance headache. A brake earns its certificate through brutal testing. In this chapter, we watch torture tests that prove reliability. On dynamometers and test rigs, brakes undergo accelerated life testing, repeated apply and release cycles at realistic loads measured in pounds, simulating decades of operation in months. Thermal shock tests heat braking surfaces to high temperatures, then cool them rapidly to test resistance to cracking and warping. Endurance tests run thousands to millions of cycles, monitoring wear rate in millimeters per thousand cycles and measuring changes in coefficient of friction. Overload tests verify that backup systems engage correctly when a primary circuit is intentionally disabled. Environmental chambers expose assemblies to humidity, salt spray, and dust to check corrosion resistance. Non-destructive tests, ultrasonic, magnetic particle, and dye penetrant inspections look for microcracks invisible to the eye. Finally, field acceptance tests involve hoisting test weights and performing full-speed emergency stops under supervision. Codes like ASME A17.1 dictate many test criteria and redundancies. The point is blunt: a brake must fail gracefully, or better, not fail at all. Installing a brake in a skyscraper requires both finesse and brute strength. Here we follow the elevator from factory crate to machine room. Rigging crews lift motors and brake assemblies into tight plant rooms, aligning shafts and coupling to drive systems. Installers anchor brake mounts to structural steel, using torque-specified anchor bolts and grout to transfer loads safely to the building frame. Wiring runs to the control panel include redundant safety circuits, monitored by the building management system. During installation, technicians set parking brakes, calibrate the governor speed, and run final leveling tests so the car stops within millimeters of the floor. Commissioning includes timed emergency stop tests under full load and verifying that the brake holds when power is removed. Codes require documentation, traceable serials, test certificates, and maintenance schedules. Finally, operators receive training on daily checks, pad wear limits, spring preload measurements, and warning signs like chatter or glazing. Installation is the last mile where an engineered brake becomes a building's anchor.
We close with the big picture. A humble brake enabled an architectural revolution. By reliably holding tons with predictable behavior, brakes allowed architects to stack floors without the heavy masonry that limited height. Elevators, controlled and redundant, transformed human movement into vertical transport systems, shrinking travel time and making dense, mixed-use neighborhoods feasible. The engineering success rests on disciplined material selection, precision machining, chemistry of friction materials, control electronics, and exhaustive testing. Today, brakes are evolving. Electronic machine rimless drives, regenerative braking that recovers energy, and advanced composites that cut weight and improve thermal performance. Yet, the core principle remains the same. Convert kinetic energy safely, repeatedly, and predictably. We leave with numbers to visualize that achievement. A brake clamping at 100% of design load, holding a car full of people, day after day, millions of cycles over decades. It is an engineering promise kept. This is how a brake helped build cities, one stop at a time.
I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.